The next thing that I would like to draw your attention to is noise in a special class of LPTV networks. So, when we were doing so this is total integrated noise in networks with R, L, C and periodically operated switches. Okay. Earlier we have seen the total integrated noise in networks with only R, L and C, right. Now, we also add periodically operated switches. So, remember that every periodically operated switch in practice basically can be thought of as having some series resistance and an ideal switch. Right, and this RS adds noise okay, and its noise spectral density is 2 kTr volt square, if it is 4 kTr volt square per hertz. This is single sided or 2 kTr volt square per hertz double sided. All right. So, for example, here is an example circuit. So, let us say we have an ideal a switch. This is the resistance of the switch and this is a capacitor, right. The question is, what is the mean square? I mean, clearly when you close the switch, the there's an the resistor has got some noise, correct. So, when the switch is closed, well, this noise goes through the network and is there on the capacitor. Some noise voltage exists across the capacitor. Then you suddenly open the switch and whatever noise there is on the capacitor remains there, right. So, therefore, there must be some mean square. You should be able to evaluate the mean square value of that noise. The average of the noise will be 0, right. So, the mean square noise must be some value and we would like to find out what that mean square value is. We have already seen this earlier in the context of sample and hold, right, and this basically what was the result? Very good. So, Vn square, the mean square noise across the capacitor is nothing but kT over C. Okay. All right. Now, the question is, if you have a more complicated network, so let us say this is some phi 1. Now, the question is, so let us say you have a switch, you have a capacitor C1, you have another switch, you have another capacitor C2, right. Let us say this is clocked by phi 1, this is clocked by phi 2. Phi 1 is something like this and phi 2 is something like this, right, and they are periodically switched. So, this is say this is Ts, right. And the question we would like to ask is, what is for instance, what is the mean square noise across C2, right. Okay. So, there are several ways of doing this, and remember that we are only interested in the total mean square noise across the capacitor, right. Okay. Now, the question is, if we are only interested in the total mean square noise, okay, it does not seem to make sense to determine all the transfer functions, which are basically functions of frequency, and basically integrate all of them to get the total mean square noise, and therefore, work hard to get a lot of information and then throwing away most of it, because you are only interested in the mean square noise. This is exactly similar to the Bode noise theorem for time invariant networks. Now, it turns out that for networks with RLC and periodically operated switches, we can use the same approach to simplify the noise, right. So, that is what we are going to be doing next. So, let us try and exploit what we know so far, namely that let us try and find, I will continue with this example. Let us try and find, let us say this is V out. Let us try and find the mean square noise, right, of this network at say some n times Ts, right. In other words, I am interested in the mean square noise at the output of the network, right. But this is the key point is that I have converted the mean square noise problem into something where I am only interested in the mean square of the sampled output of the LPTV network, correct. So, in other words, therefore, you can basically use all our results on reciprocity as well as the equivalent LTI filter, right. So, what are the noise sources? Vn1 and Vn2, correct. So, therefore, we have Vn1, it goes through H equivalent 1 of t, which is an LTI filter with an impulse response which is H equivalent 1 of t, correct. Vn2 likewise goes through H equivalent 2 of t, correct. And then you add these two, okay, and you sample the output, and that will give you V out of NTS. If you sample it at n times Ts, you will get V out of NTS, correct. And therefore, what is the mean square noise of NTS? You simply integrate, it is basically the noise spectral density. Let us assume that Vn1, this is a switch. So, this is nothing but 2 kT R1 integral minus infinity to infinity H equivalent 1 of j 2 pi f whole square df plus 2 kT R2 integral minus infinity to infinity H equivalent 2 of j 2 pi f the whole square. All right. Now, by Parseval's theorem, okay, so it does not matter whether you integrate in the time domain or the frequency domain. So, this becomes the same as integral 0 to infinity h equivalent 1 square of t dt plus 2 k t r 2 integral 0 to infinity of h equivalent square 2 dt. All right. All right. Now, how do we find the h equivalent 1 and h equivalent 2? We know how to do that already. So, remember this is our network. So, this is R 1, this is V N 1, which corresponds to the resistance of the first switch. This is capacitance C 1, V N 2, R 2, this is phi 2, right. Okay. And well, to find h equivalent 1 and h equivalent 2, what will we do? Our input is a voltage, the output sampled output voltage, we are sampling it at t equal to a timing offset t naught, which is equal to 0. So, what do? We need to draw the adjoint network. So, this is phi 1 hat and phi 2 hat, right. We remove these noise sources, these are all now 0 volt sources, correct. What do? Apply a current impulse at t equal to 0. So, this is delta of t, correct, and therefore, the current that flows through these voltage sources will have a shape that is similar to h equivalent of t, right. Okay. Remember that this is a whatever flows in these sources is a current, right. But to get h equivalent of t, you have to divide that current by 1 coulomb, correct, which is 1 ampere second. So, that you will get the h equivalent 1 of t, correct. So, similarly, this is h equivalent 2 of t times, remember this is a current. So, this must be the current that you see will be this times ampere second. Does it make sense? Right. And the reason is that this is a current and it will have the same shape as the impulse response. Okay. Now, what comment can you make about the energy dissipated in the resistors is what?
Voltage across the CT initial is 1 by CT.
No, that is okay, but in terms of the currents flowing through them, what comment can we make about the currents about the energy being dissipated in the resistors? Yeah, it is simply h equivalent 1 square t dt times R1, all right, plus R2. This integral has to go from 0 to infinity. This is nothing but integral 0 to infinity h equivalent 2 square of t dt correct, and this must be equal to
half 1 by
well
2 CT.
The impulse that you apply across the output port, right, will inject some energy E0 into the network at t equal to 0. So, this is nothing but energy in, so if this is the network n, this is the network n hat at t equal to 0, right. So, then as the network keeps running, well, there is something happens to the energy at t equal to infinity. There must be some energy in the network at. Now, all this, remember, applies to the adjoint network at t equal to infinity. Okay. So, the difference between the energy at t equal to 0 and t equal to infinity must be exactly the
Whatever the dissipated in
must only be dissipated in the resistors. It cannot be dissipated anywhere else, because the capacitor is lossless. If you had an inductor, that would be lossless. This is an ideal switch, right. So, the switches are lossless. So, the only place where all this energy can be dissipated is the resistor, right. So, therefore, we have seen therefore that E infinity minus E0 minus E infinity must be this, but what are we trying to find? What we are trying to find is this quantity here, which is simply 2 kT. I mean, you can think of this as being proportional to energy dissipated in R1, and this is energy dissipated in R2. Okay. So, what do you say? I mean, what therefore can we say about the mean square noise?
can apply the 2K.
Mean square noise V out is nothing but 2 kT times E0 minus E infinity, right, by 1 Coulomb square, right. Why is that? So, this is actually
We are using the current.
Coulomb square, and this is must also be multiplied by, actually I will call this ampere second. This is also ampere second, all right. Okay. So, the mean square noise of the output sequence sampled at n times Ts is simply nothing but E0 minus E infinity by 1 Coulomb square. This is exactly the same form that we got for the time invariant network. So, whether it is time invariant or periodically time varying, we get the same result. Okay. Now, this is, I mean, remember this V out of the mean square value of the output sequence sampled at integer multiples of Ts. and this must be stationary because it is not varying from, it is the output, you can think of it as the output of a linear time invariant filter, and therefore, this is basically not changing from sample to sample, right. Now, what comment can we make if we wanted, so to summarize therefore, if you have a network with R, L, C and periodically operated switches, and you want to find the mean square noise, of the sequence. So, okay. What do? You first form the adjoint network. So, to do that, what do you do? Well, you form the adjoint. So, you have to time reverse the timing of the switches, that is the only thing that you need to do. Then you inject an impulse current here, right. E0 is the energy in n hat at t equal to 0, E infinity is the energy in n hat at t equal to infinity, and mean square value of NTS is simply 2 k T times E 0 minus E infinity by 1 Coulomb square. All right. Now, let us do some examples. So, I am showing switches here without the resistance, but every switch is associated with a resistance. This is C2, this is phi 1, this is phi 2, and we are interested in the mean square noise here. So, what do? We form the adjoint, right. You apply a current at t equal to 0, right. So, what is E 0? 1 by, so if you inject a 1 Coulomb charge, 1 by C2 is the voltage developed. So, this basically becomes 1 by 2 C2, right, q square by 2 C. And E infinity, what is E infinity? Well, there is a voltage developed across C2. It when phi 2 hat is is high, the charge is shared between C2 and C1. Then C1 is connected to ground. So, C1 will discharge. So, as you can see, eventually charge is getting from C2 and also C1. So, eventually both the capacitors will have 0 charge and therefore 0 energy. So, E infinity must therefore be 0. So, the mean square value NTS is nothing but 2 k T times 1 over 2 C2 minus 0, which is nothing but k T over C2. All right. Now, okay. Now, what comment can we make if for instance, if we wanted V naught square of mean square value of NTS plus T naught, what would we do?
We have to apply the impulse at the T at T naught. We have to
No.
like it's like T plus T minus T naught. We have to apply.
What is T?
Sorry, delta of T plus T naught.
You have to apply delta of T plus T naught. So, you have to apply the impulse at what time?
At minus T.
At minus T naught, correct? So, so in this, if you apply the impulse at minus T naught, what is going to change?
Initial, like we have to find the initial charge.
Yeah, the initial charge. So, what happens? The only thing that changes is that, I mean, this switch, right, which is basically is either an open switch or closed switch with resistance Rs, correct? In either case, what comment can we make about the voltage developed across C2?
That is 1 by
It is always going to be
1 by C.
1 by C2, 1 by 2 C2. I mean, sorry, the voltage developed across C2 is going to be 1 by C2. So, the initial energy is going to be E0 is still going to be 1 over 2 C2. E infinity is going to be 0. So, the mean square noise is going to be kT over C2, right. So, regardless of when you sample the output, the mean square noise is always going to be kT over C2, all right. Okay. So, let me take one last example where E infinity is not 0. Let us call this C1. This is C2. This is C3. Okay. So, what is the mean square noise here? Let us say of NTS. What will we do? We will form the adjoint, then so that basically is phi 1 hat, phi 2 hat. Then we apply an impulse here, delta of t. What is E0?
1 by 2 C3.
Yeah. So, when you inject an impulse, the voltage across C3 is 1 over C3. So, E0 is nothing but 1 over 2 C3, right, which is nothing but half C3 times 1 over C3 the whole square, right. Now, once the network starts, I mean, you know, you let the whole thing operate, what happens at t equal to infinity?
Total voltage at all the capacitors should be equal.
Yeah.
Charge distribution.
Very good. So, in steady state, the voltage across all the capacitors is identical, right. Okay. So, Vc1 equals Vc2 equals Vc3, and what is that voltage?
That initial voltage.
Initial. See, there is nowhere for the charge to go. So, whatever charge you put in initially, which is 1 coulomb, will be distributed across 3 capacitors, and all the 3 capacitors have the same voltage, right. So, the voltage will be 1 divided by C1 plus C2 plus C3 across all the capacitors, right. So, V infinity across all capacitors. right. So, what comment can we make about E infinity therefore?
Like 1/2
Half into C1 times V infinity the whole square plus C2 V infinity the whole square plus C3 V infinity the whole square, which is nothing but 1/2 into C1 plus C2 plus C3 times V infinity the whole square. So, this is nothing but 1/2 times C1 plus C2 plus C3, all right. So, the mean square output noise is nothing but kT times 1/C3 minus 1/C1 plus C2 plus C3. Okay. So, therefore, thanks to this observation and energy conservation, just like how we saw in the case of linear time invariant networks, the process of evaluating the total mean square noise can be done actually by simply looking at the network without calculating any transfer function at all, correct. You know, as you keep, I mean, here is one final example. So, let us say this is phi 1, this is phi 2, this is R, this is L, okay, this is C 1 and this is C 2, right, and we are interested in the mean square noise here. What would this be by inspection?
KT by C.
It will simply be KT over. So, E0 is nothing but 1/2C2, E infinity is 0, right, and therefore, mean square noise is simply KT over C2 and does not depend on L or C1 or R or anything else. Okay. So, with that I will stop.